So our next speaker is going to be from Nanalysis. Susie Riegel will talk about advances in benchtop NMR and recent industrial applications.
Yeah, thanks very much for the introduction. It is my pleasure to be here to talk a little bit about what we've been doing. Apologies for the last minute change, but just due to some scheduling conflicts, I had to step in for my colleague Juan Arenada. So I think probably most people are familiar with Nanalysis at this point, so I won't go too much into detail. But Nanalysis is a global manufacturer of portable NMR technology. We started in 2009 with headquarters in Calgary, Canada, with a core competency in making highly homogeneous permanent magnet arrays. In 2020, we acquired RS2D, a leading manufacturer of NMR electronics, headquartered in Strasbourg, France, to help expand the amount of features that we could offer on our benchtop NMR product line. In 2021, we acquired One Moon Scientific to help add some software layers for automated data analysis for our industrial customers. And then in 2022, K-Prime to extend our sales and service arm. Our main product line is in portable benchtop NMR technology. So our flagship product was an all-in-one 60 megahertz instrument that's available in proton only or multi-nuclear type configurations. And then we also announced a 100 megahertz product as well. So the vision for these is that they are easy to sight, compact and portable. So they have built-in touch screens. But of course, if people would prefer to have computers, they can be controlled locally from an external computer or remotely, whatever the sampling kind of requires. We're standard JCAM-DX format, so we're compatible with other third-party software providers and pretty easy to work into any sort of automated analysis flow. And they come with a series of potential accessories, software features, etc. So why the renaissance of low-field NMR spectroscopy in the form of these smaller benchtop NMR packages? And the reason that we think that there's a need for this is if you look at the global distribution of NMR, so this is from an SDI Global Assessment report, you can see that there is a strong stratification of NMR in the world, where sort of the richer northern countries have the majority of the NMR instrumentation. This actually gets worse if you look at it a little bit more granularly. So 8 countries, so less than 4% of those worldwide have 80% of the NMR instrumentation. So as we become a more global economy, pharmaceuticals get outsourced, emerging materials come from different locations, we need to start addressing that access to NMR spectroscopy. Additionally, if you look at the end user distribution of NMR, about 76% of it takes use of the qualitative structure elucidation applications. Obviously, I don't need to tell this group that NMR is one of the most information-rich techniques that you can have. So, of course, drug discovery analysis is very important. But it's inherently quantitative as well, and that is not really being exploited in a good way in industrial kind of assays. So I don't think I need to go into the physics that sort of govern high field versus low field NMR. I think this group probably understands that very well. But where is benchtop NMR positioned within the market sector? So if you kind of think of the magnetic resonance technologies, on the low end, we've got relaxometers, and on the high end, we've got high field NMR. So most people in chemical synthesis, academia, government, industry are very familiar with high field NMR spectra. So 400 megahertz to even 1.2 gigahertz, we can do increasingly complex things, look at primary, secondary, tertiary structures, absolute configuration of smaller amounts of things like natural products, et cetera. But they tend to be pretty expert and not really deployed in the sort of a large type forum. In industry, on the other hand, depending where people are, relaxometers are pretty well known. If you were in the food science industry, for example, solid fat content analyzers for bulk property for cheese and dairy and things like that are very common. So what we do is we position sort of benchtop NMR right in the middle. So we're high resolution, we can speciate, we can determine J coupling constants. So for smaller molecules, for people that have less stringent requirements, it absolutely can fill the need of the underserved users of high field NMR. But it's in a small enough package that it can be dedicated to a specific analysis. So our vision is to work on growing the instrument out of just the underserved users, like those in chemical education or startup, small, medium-sized chemical synthesis companies that maybe economically can't justify having a dedicated instrument, but don't want to waste the time it would require to outsource every one of their samples when they're doing things like, is my reaction complete? Is my solvent pure? Type analyses. So this is sort of what the user landscape of Benchtop NMR looks like today. The underserved users and illicit drug detection to help look for non-targeted methods to identify illicit drugs. And we think the real growth potential for Benchtop NMR is in exploiting the quantitative applications that are available. So reaction monitoring process analytical technology, of which has already been touched on here this morning, determining dosages in illicit drugs as well. And then what I'm going to talk about for the majority of this talk is the development of quality assurance, quality control type applications. So we do this in a threefold approach. The first is method development, method validation. So we either look at bringing in emerging new products or chemicals and that don't currently have assays associated with quantifying their key parameters, or modernizing ones that already exist. So things that have been around for a really long time, maybe they're using wet chemical methods or something that's not really optimal to determine that variable. And then we do things like optimized pulse programs, which I think Manuel did a great job at sort of explaining some of the work that goes on there, adding signal processing, Jose with the data analysis, things that you can use like Craft or SPAC to be able to automate and get more information out of the spectra than you maybe previously were able to. Part two is productization. So we all have existing what the instruments look like, but we really need to find a solution that will fit a specific industry. So whether that's the performance metrics need to be changed, the ruggedization of the instrument, maybe the form factor needs to change, the sampling method, the connectivity, et cetera, to really have that market pull and meet the market requirements for a specific assay. So we need to work with key stakeholders to make sure that we have a minimum viable product that has been identified and it meets all the regulatory requirements and data integrity. So whether that's in pharmaceuticals, CFR 21 Part 11 compliance, or just a standard GXP kind of mentality. So if NMR is used primarily for R&D and exploration work, what are the typical things that we use for quality control? And the most commonly used is chromatography. So either HPLC or GCFID, GCMS. So these are very well known in the testing methods. And then occasionally we still see a lot of wet chemicals, things like titration. So as Jose was saying, high-field NMRs are great. Obviously, there's a ton of information in there. They can help build models, but it's just not feasible to have them dedicated to QA/QC, whether it's a size problem in the lab or just the cost associated with that. So this is really evident in the testing and method group. So if you look at regulated methods, they rarely include NMR spectroscopy as the value for the assay. So you could see this with everybody, but just as an example, the United States Pharmacopoeia has over 5,000 monographs that are available to provide information about how to analyze APIs, excipients, et cetera. And less than 0.4% of them even mention NMR spectroscopy, and less than 0.2% of those are QNMR. So this can be also mirrored with all of the other geographical bodies, Europe, Japan, also ASTM International, AOAC International, International Standards Organization, et cetera. For people looking to use third-party companies to develop these methods as well, we see the same thing. This is a bit of a digression, but it's very hard to find NMR spectroscopy as an offer in these kind of testing labs. So by no means a comprehensive view of everything BioVeritas offers, but if you look up NMR spectrometry, relaxometry, proton NMR, all you get is no results found. Intertech, on the other hand, they do have NMR, but it's kind of buried. So you see that their global analyticals has chromatography as a section, spectroscopy is a section, but then in this list, they also have the specifics of mass spectrometry. If you click on spectroscopy, you can bring out your analysis where it has things like FTIR, near IR specifically listed. And although those are all molecular spectroscopy type techniques, they also have a molecular spectroscopy section where if you click on that, those techniques are renamed and NMR is there. So it's really hard for people and companies that don't have a lot of NMR expertise to even look at incorporating NMR, regardless of what the value might be there. But of course, we are very keen in doing that. And I think the NMR community is very keen on doing that as well, because we know about the power and how useful that this technique can be in industry. So this is typically what we see. Chromatography is the most commonly used thing. It can see very low quantities. It can do very ultra pure profiles, but it's not necessarily ideal. It uses a lot of solvent, which is not very environmentally friendly. It costs a lot to buy that solvent. It costs a lot to dispose of that solvent when you're done with it. Obviously, you can optimize your analysis, but they also typically have pretty long runs and require a lot of maintenance to be able to use them. FTIR was sort of miniaturized a while ago, and we are seeing more assays that use FTIR. But one of the main problems with it is that it really has to be model-based, and you have to have very specific model analysis to be able, so any changes in composition, et cetera, really change your results. And so most of the people that we talk to in industry use FTIR as like a screening tool, but rarely a confirmational standalone tool to be able to do their analysis. So high field NMR would be perfect, obviously, with the data quality that we get from it, except for the cost of being able to do that. So this is really where we position NMR spectroscopy. So we are seeing more interest in the industry of incorporating that. And I think like the work that Jose is doing there is very exciting. It's some of the more forward thinking that we've seen in a lot of the industry analysis. But there is a lot of hesitation. So a small digression here. I was reading this QNMR handbook that the QNMR Summit group just published. And in the foreword by Dr. Dial, he said that he sent his an NMR method to one of his colleagues, and the email response was, an analyst would rather use his colleague's toothbrush than his NMR method, which kind of made me laugh, but I really think highlights the view in industry of how people are using this technique. So he goes on to say that there's a distrust of NMR among methodologists in HPLC labs and elemental analysis, which kind of makes sense. Nobody wants their technique to be displaced. But the main problem is that there's also a little bit of distrust from the NMR community itself. We've spent so much time developing really sophisticated pulse sequences that we've overlooked that like a 1D proton can give you a world of information. So really want to push the value proposition of how NMR can, by no means sexy applications, but can be very useful. So I think Manuel highlighted this very well. It's non-destructive. We can reclaim our sample after. We can test it again if we need to. It's very simple sample preparation. You're not doing serials dilutions. You don't need a bunch of other things like that. It's non-targeted. So maybe you have a composition mixture. You can quantify everything in that mixture with one experiment. You don't have to write a series of assays to get every single one of those variables. And it can be a lot more environmentally friendly. So one more digression, again, not the most exciting slide, but I think very important, is since starting at Nanalysis, we have been asked to work in a number of different round robins on interlaboratory studies, but more or less this doesn't exist for NMR. It's an analytical technique that is not quantified as an analytical technique very often. So most of the work that we do, we try to focus on how we can quantify everything and make sure that we know it is truly an analytical technique. So this is a paper that we recently published following the interlaboratory study requirements from ASTM. We had 5 analysts each prepare 5 samples by just looking at one paper of an SOP on how they should prepare their sample, knowing nothing else about it. We ran those in triplicate and then ran them on 23 instruments spread over our different campuses. We then followed the statistical analysis that was outlaid in this paper. And I just wanted to highlight, there's a lot of information in the paper if you are interested, but I think these two, the Mendel statistics are pretty interesting. So the first one, the H variable, looks at between laboratory comparisons. The dotted line there represents the 0.5% statistical analysis. HPLC often fails in this because you see very differences between instruments, locations, and analysts. And you can see that there's no outliers. We see no systematic error. There's negative and positive results, and it compares quite well. And then we can also do the interlab where we looked at one analyst. And again, you can see very good results on different days, different samples, different temperatures. So we know that the instrument's analytical, and we try to do a lot to quantify how analytic it can be from different things. So for the remainder of the talk, I'm going to focus on some of the method development that we've been doing. So the first one, I'm going to say new method development. So this is an emerging product that doesn't have an analyst tools that are already used for it. It's lignin, of course, a standard byproduct of the pulp and paper industry. It's found in the cell walls, and it's an irregular organic biopolymer. So it could be potentially used for a variety of things, like energy, concrete, and then also a building block to replace a lot of the starting materials that we get in the chemical synthesis industry from petrochemicals. So this is a representative of what a lignin structure might look like. It's very complex. It's a total nightmare. Proton or carbon, 1D, 2D NMR would be a nightmare on really any field. You couldn't get a lot of data out of it. But if you can do some sample prep, so this one is a phosphorylation method, we can use phosphorus NMR as our NMR handle. So we can digest this, make some phosphates. Phosphorus is, of course, 100% natural, abundant. It has a very large chemical shift range, and it has really sharp lines. So I'm not going to go into too in-depth in this, because after the break, Dr. Ian Burton from the National Research Council of Canada is going to talk about this method development. But I wanted to highlight it because it has been submitted to the Canadian Standards Organization and accepted. So it is approved method for analysis in the lignin industry for 60 megahertz or higher. And we're also going to submit it to the International Standards Organization to make it a little bit more global. The second one is modernization of an existing method. So these are products that exist, and they have assays that are recommended to get those technical values out of them. And they could be quite large markets. So the example I'm going to highlight is chitosan. It's currently valued at about 1.2 billion. It's found in mushrooms, hard-shelled insects, aquatic crustaceans, things like that. And it's typically the chemicals from the shells are worth more than the initial product that itself, but it's just a better use of the whole shrimp that or whatever that is removed from the ocean. So it has a number of potential uses. It's antimicrobial, it's an antioxidant, but the most common is that it's an excipient that can be used in drug delivery. It's also thought that it might have health benefits for reducing cholesterol and fat loss, but I don't think any of that is sort of verified at this time, but it's also used in the nutraceutical industry for those reasons. So the key parameter in the drug delivery is what's called the degree of deacetylation, so the percent DDC, and that has the value on how that product works and how it delivers the drug. So again, just to keep with the theme of why Benchtop NMR. Well, currently today, Ecuador is one of the largest shrimp producers in the world. This is where the majority of chitin, chitosan comes from. But Latin America has less than 2% of the NMR spectrometers worldwide. So to even outsource that, it's very difficult. And typically they have to use titration methods, which are quite timely. So proton NMR can be very easily used to determine the degree of deacetylation. So we perform this according to a USP monograph. We're looking at the relative comparisons of the A1 versus A2 molecules that are highlighted there in my chem draw. It's a pretty fast experiment. The monograph itself calls for the use of deuterated formic acid. So we showed that with a comparison initially, but that obviously is another good way where you could save a lot of money. So we've shown full equivalency with no effect to the statistical analysis by changing out deuterated formic acid for Proteo, and you go from about $100 per sample to about a penny per sample. So again, not a very exciting spectrum. You can see what it looks like at full view, and then you can see the zoom in there. But we're just looking at the ratio of A2 to A1 for that degree of acetylation. We've done it for a number of different chitosan products, and you can see that we have 60 megahertz data compared to the high field 400 performed by the monograph, and then the reported that came with the chemical we had. We have higher relative standard deviation on the low field NMR, probably due to the signal to noise. As you can see, they're kind of in the baseline there. But still well within what's sort of acceptable from the monograph itself. And then finally, I guess I'm going to touch on what Jose talked about, and that's can we take the modernization of methods even further and move towards more of a digitalization? So the prevalence of liquid chromatography in the industry we use a lot of wet chemicals. You need ultra pure standards that need to be identified, that need to be purchased, and it limits the applicability and the like comparability of data on a global scale. So there's a number of ways you can do it. Chemiometrics is one. And the other one, of course, is quantum mechanical modeling. So we've also used NMR solutions in this way, but I'm going to talk about the work that we did with USPID using chem adders, quantum mechanical modeling. So I'm by no means an expert in quantum mechanical modeling, so I'm not going to teach it to you, but basically what it does is it uses the essential NMR spin parameters, so chemical shift, coupling constant, line shape, to predict what the proton NMR spectrum should be and fit it. And the reason that this is key, I think, is because it's independent of field strength. So you could have a model at high field and run it at low field, or if you had acquired, like you have a database based at 100 megahertz, you could still use it on your 400 or your 80 or your 42, whatever you're able to extrapolate between the fields. So it uses adaptive spectral libraries, so it fits the whole spectrum simultaneously, which is also key because typically when we're doing an internal standard, we only use one signal. So you often see a bias in the results, which is more or less eliminated by the use of quantum mechanical modeling. So it really reduces the user's influence on that quantification. So we have another examples of this that you can find in the literature, and I'm happy to talk about, but this is a publication we have coming out very soon, just over-the-counter painkillers. So we've done this for a number. The one I'm going to highlight for the rest of this talk is a headache branded, marketed Tylenol that contains acetaminophen and caffeine. The USP method uses titration. The USP method uses HPLC. So I just have a snippet of the assay there. Nothing really for you to read, but it requires the use of methanol, glacial acetic acid, water, benzoic acid, ultra pure standard caffeine, ultra pure standard acetaminophen. So obviously we can do that with one NMR. We're going to use one internal standard. It's the ethylene carbonate there. You can see the peak labeled 10. It's very well resolved. We can integrate those easily. So this is a well-resolved spectrum, minus you can see that there's some water overlapping in the caffeine peaks in the 8 to 9 region that might limit our quality, but we do have a distinct caffeine peak that we could just use on our own. So basically what we did is we took the assay HPLC. So I've anonymized these, but there's 3 generics and 1 name brand of the medication. We've done the HPLC assay on one of them for direct comparison, and then we're comparing standard integration QGSD from MNOVA, as well as USPID also implemented in MNOVA. And you could see that there's really good agreement between the NMR and the HPLC, slightly lower standard deviations by using this quantum mechanical modeling because it's pretty well resolved, but we usually see those if there's substantial overlap. Very good and very accurate for both the acetaminophen and the caffeine, which have an acceptance criteria that's surprisingly high, I would say, but it's 500 plus or minus 50 milligrams of acetaminophen, and then the caffeine is 65 plus or minus 8. So you see good agreement, and the USPID really shows that the relative standard deviation can be reduced by using the quantum mechanical modeling. So just to conclude, again, sort of focusing on why do we want to do this, and it's why is there a value proposition for NMR in industry? So this changes obviously per assay, and Benchtop NMR can't be used for every assay, but this one specifically. If you're looking at capital cost, an HPLC is going to run you about $115K, and that's going to include your IQ, OQ, your automated software, maybe your databasing, and your NMR is going to cost you about $50,000. So you're saving yourself almost double the cost in that initial purchase, but then it really compounds in the operating expenditure. So if we look at consumables, I have them listed here. So your column, your methanol, your glacial acetic acid, your water, your deuterated solvent, your solvent disposal, your column flushes, your vials, standards, et cetera. To run 100 samples on HPLC is going to cost you about $4,000 and about $35,000 to run 1,000 samples. For the Benchtop NMR, it's going to be about 1,000, about 12,000 per 1,000 samples. So you can see that that really compounds over time. And with the maintenance requirements, operating procedures for HPLC, this even gets worse as you maintain it and the instruments age. And then, of course, also analysis time. So you're doing about a 45-minute elution in this specific example. So to run 100 samples, you're taking about 52 hours versus 8 hours on the Benchtop. and that extrapolates, of course, linearly. So hopefully I've shown you that Benchtop NMR is a suitable technique for the quantification in a number of QA/QC industries. The analytical data is quite compelling to suggest that NMR can be used in this matter. And there's a lot of reasons why we should do it. But we need to sway key stakeholders in the industry to get a better sort of understanding of how the value that NMR can provide. So thank you very much for your attention. Thank you for inviting me to speak here. I'd like to thank some of the people who did this work from FP Innovations, NRC Canada, who you'll hear after the break, Kytolytic, and USPID. Thank you.
So questions?
So this is specifically the what is used in the assay that's required. But you're saying for NMR, you can use water?
Yeah. You could use what is it?
You could reduce it. You could optimize it, perhaps. Yeah.
Oh, I have a question.
Yeah.
I'm not really familiar. Well, how do you, when you talk about quantum mechanical modeling, how does that figure into an analysis? I mean, you're calculating the spectrum of something, and does that then, what does that lead to you
So
to?
So it depends on the software provider
Yeah.
itself. So I don't know if anyone from MNOVA or Master Lab is here, but hopefully they'll do a demo of USPID. They have a library based on every compound that's in one of their monographs. So if you're running a monograph of any kind, it'll search that library and fit it. So basically, when you're doing quantum mechanical modeling, usually you run like a pure sample on 400. And it'll extract what it thinks the chemical shift, coupling constants, line shape is, and store that data. So when you're running a new sample that's an unknown, it will then predict the spectra and fit it over based on the coupling constants and chemical shifts.
So does this replace going into a library then?
So it's just another way of
It's another
looking at
way
the library.
In addition to looking to a library.
And then you're not limited where you're trying to apply a 90 megahertz spectral library to your 400.
Yeah. Okay, other questions? Yes.
I mean, it's hard to create momentum, right? Like people do what they've always done because they feel comfortable with it. And when you have to have something that's very hard to explain to people, right? Like people kind of understand optical spectroscopy. People kind of understand like those kind of techniques, but explaining NMR to people is challenging. Like, I am like do a lot of talking to investors and things like that, and people do not understand the very basic concepts. Like you almost always have to say like, it's MRI for chemists, and then people will kind of get it. So I think it's a knowledge issue. And because it's never really been used in industry, typically you'll find somebody technical who's kind of pushing things, but then they have to be able to sell that to the various other stakeholders in the industry. And depending on how good of a job they can do at that, or how much data they have, it's really hard. Yes, yeah.
NMR method like this into the ESP, because it seems to me that's what the main push will be, right? Because you're using something which is not in ESP,
So no, I mean, you have to do the analysis. So we do a lot of the analytical things, and then you submit it to them for review. Like none of the regulatory bodies work very quickly. So we have a lot of sort of irons in that fire, but how long it takes to get things approved and published is to be determined. So they're open to review these things, but it can take a while.
Jose, you had a question before? Yeah, go. Thank you.
No, I just wanted to expand on what Susie just made a statement about how difficult it is to change somebody's thought process. And I think to some extent it's also true among us. When we say automation, what we say is do whatever I am doing in an automatic fashion.
Yeah.
We don't think back and then say, how do I do this better? I'm not saying we don't, I'm just saying we ask that question, that kind of question less. And we ask the question of, I do these things in order to get to my result. I want to automate this. The classic example, my pet peeve, is how many papers are there on phase correction and baseline correction. I'm not going to.
Yeah.
comment on that.
Yeah, frequency domain has done no help in the quantity of data analysis. There's no question there. Uh, That's for sure. I think like the NMR community itself is like NMR is such a cool technique, and conducting those nuclear spins to give you very specific results has made so many cool pulse sequences and things that the NMR community itself isn't focused on the inherently quantitative nature of a 1D proton NMR spectra. Like that's not cool, right? And so I think that's the other problem is the experts are focused on expanding the area from a structural elucidation perspective, but not from a quantitative perspective.
Just wanted to say, very nice presentation, Susie, and I will show this to my manager.
Thank you.
Going back to what Dan was saying too, yeah, I mean, once we reach critical mass and most of these instruments are available, you will see more applications coming. One of the problems that we run into is that we might develop a method on the NMR and then we have to transfer to a contract organization and they don't have an NMR. And everybody has an HPLC. But you can see now that the costs are getting comparable or better. The other thing that I can tell from our experience is that obviously HPLC method transfer has been done for many, many years and it works. It might not be trivial sometimes. QNMR method transfer is very, very straightforward. It requires a documentation, but in terms of the design and the information that you have to share, is probably a fraction of what you have to do for an HPLC.
More questions? So one question that I have, you went to that Tylenol analysis
Mhm.
where in my mind, it seems like a no-brainer. All those solvents injecting and you just put your sample in an NMR spectrometer and analyze it.
Yeah.
How often would that analysis be done in a normal industry setting?
So, I mean, maybe Jose can answer that
Yeah.
better than me, but so from my understanding is a lot. So you'll make a batch sample, you'll formulate the pills, and then they'll do spot tests of a few of them to make sure that they're all within the acceptance interval.
Okay.
And when they use HPLC, there's a dedicated HPLC at the line that they would use exclusively for that one analysis.
So, I mean, that would be the same way that they ought to be using a tiny little NMR instrument.
Exactly.
The main difference is that if you have different formulations, there's going to be some effect on the HPLC. There's going to be more peaks. The retention might be affected a little bit. With what Susie is showing is that those, as long as you're using the same conditions and the same solvent, those peaks are going to be always there. And even if there is overlap with the QMSA approach, you can still fish them out of the overlap. With the quantum mechanical approach, you can still get them.
So it seems like you ought to be able to have a drop in the sample output as opposed to a lot of chemistry.
Absolutely.
Yeah.
Yep.
So any more questions? Okay, well, thank you, Susie.
Yeah, thank you
for
very much.
exciting talk.